Welcome back. Guys, we've been looking at tree diagrams, investigating these different types of events. And in particular, we've been focusing on independent events represented in a tree diagram. In this example we're going to look at dependent events. So on our concept map, remember that dependent events are those that are not influenced. So the probability of A is in fact going to influence the probability of B. They are related. There's going to be a change. Because of this one is going to change. Whereas independent, there is no relationship between the probability of B and the probability of A. They are not related. If B happens to be a certain number, A can still happen to be whatever it likes. There's no requirement that the one comes first or the other one comes first. They're going to be as if the other one doesn't exist. That's why we say they're independent. And remember, for independent events, we can recognize that we multiply those two things together, and that will give us the intersection of those events. Right, let's make sure we can apply this now to a tree diagram. And the tree diagrams that we've been dealing with, we've all recognized that they had a certain amount of independence. But in this case, because there is no replacement, we recognize this is a clue for independence. But let's get into the detail. So we're told we've got 3 red balls and 5 yellow tennis balls. What we recognize is that this player picks up the balls at random. So there's no order here, there's no preference. And she then picks up the ball, she puts it to one side, and then she does not replace it. She doesn't put it back into the bag, and then she picks up a second one. Now, we're asked to draw a tree diagram to represent the above, showing all the possible outcomes. And so that's exactly what we're going to do. So let's go and do this, draw the tree diagram, and fill in as much detail on the tree diagram as possible so it will help us with any further investigations or calculations. So the first thing we need to recognize, I've already set it up. At the starting point, we recognize that we can either have a red tennis ball or a yellow tennis ball. And so I've got the red over there and the yellow over there. And that's where the branch takes place, because it can either be red or yellow. Remember, these aren't some sort of in-between road that you can get half red, half yellow. These are mutually exclusive. They don't exist without them. It's definitely separated between the two. They're disjoint, either the red ones or the yellow ones. Now, how many tennis balls do we have in total? Well, the sample size, the number in the sample, is going to be 3 plus 5, which is 8. So this tells us not only are they mutually exclusive, but they're also complementary, because if we have the probability of the 3, we'll recognize the probability of the 5. Those will add up to 1. Be very clear about that. So let's put in the probability of the red ones now. So we recognize there 3 red, and there were a total of 8 in the sample space, and we recognize that's 3 out of 8, whereas in terms of the yellow ones, there were 5 yellow ones, and that's 5 out of 8. Now, if we add those together, can you see it will give us an answer of 1? And that's exactly what I was going on about just now, that these are both mutually exclusive and, in fact, complementary events. It's important on a T diagram to recognize at each one of the junctions, you will get those probabilities adding up to 1. And that's the way you can check that you've got the answers correct. When we go along a stem to get the final probability, we are going to say it's this one and that one, and whenever we have an and, we multiply. So let's make sure that we've got this correct now. That was our first dip into the bag. In our second dip, and for our second dip, I'm going to change the color, we recognize there wasn't replacement. So if I chose a red ball, the probability of choosing the red ball was 3 out of 8. I've chosen the red ball. What does that mean? I've no longer got 3 red balls. I've only got 2 of them because I chose a red ball. And how many do I have in total? Well, I've taken a ball out of the bag, so there are no longer 8. There are now 7 in the sample space for the second sample space. So this is 2 out of 7. And if we go to the yellow ball, remember in the first case, I chose the red ball. In the yellow ball, there were still 5 yellow balls left. So, but in total, there are 7 balls in the bag. So if I happen to choose red and then yellow, it would be a probability of 3 out of 8 multiplied by 5 out of 7. The reason the 7 has gone down is because there were fewer balls in the sample space. I hope you can see that the outcome of the first event affects the second event. The probabilities are no longer exactly the same. If there were independent events, we would see that that wouldn't be the case. Now, let's move on and recognize the following thing. What about if we chose the yellow ball to start with? So I've chosen a yellow ball that's on this stem, and I now choose a red ball. Well, that means that I have 7 balls in the sample space, and I didn't choose a red ball to start with. So if I'm going to choose a red ball, in this case, the outcome, there's going to be a probability of 3 out of 7 of getting that red ball. But what about if I've chosen a yellow ball and I choose a yellow ball the second time as well? Well, then there were only 4 yellow balls left, and there were 7 in total in the sample space. So, guys, I want you to see now that if I'm going to calculate the overall probability or the outcomes, I can put those onto the tree diagram and then do the calculation. So that's my next step. In each case, in each time the branch split, notice vertically they added up to 1. Just like I showed you over here. These ones add up to 1, these ones add up to 1, and so we're on track. This option over here gives me the option of a red-red. This one is a red-yellow. This one is a yellow followed by a red, so it's yellow-red. And this one is a yellow-yellow. So just to help us and to make sure that we understand, how are we going to find the probability of each of those events happening? Because remember, it was this one and that one. And whenever we have an and in a tree, we've got to multiply. And so that's exactly what we're going to do. So the probability here is going to be 3 over 8 multiplied by 2 over 7. This one is going to be 3 over 8 multiplied by 5 out of 7. This one is going to be 5 out of 8 multiplied by 3 out of 7. And this one is going to be 5 out of 8 multiplied by 4 out of 7. Okay, let's get the calculator up and let's make sure that we can get these values. So clear it, and then let's go 3 divided by 8. I'm going to do it into the fraction button. It's going to be a little bit easier, I think. 3 divided by 8. 3 divided by 8 multiplied by the fraction again. We want 2 out of 7. So we're going to say that's 2. 7 goes underneath. And we're going to say, what is that probability? That gives me a probability of 3 out of 21, which is 10.71%. So I'm going to write that 10.71%, or 0.1071. I'm going to write it as the percentage, 10.71%. Now guys, I can carry on and do all of those calculations just using the calculator. I'm not going to waste time doing that. Let's have a look at what the next question is, because we might not need to do all of those calculations. Here we go. It says determine the probability that the player picks balls of different color for the two selections. Okay, so there are two ways to do this, and I want to show you both of them. They need to be of different color. Now, unfortunately, I've already started to calculate when they're the same color. That's a pain. But you know what? There's a trick thing that we can do to make sure that we've got it sorted out. And this is what I'm going to do. I'm going to calculate when they're the same color. And then I'm going to apply the complementary rule. Because remember, these are complements of each other. And so we can use all the elements in the sample space, we know that's 1, and subtract when they were the same color. And what we'll be left with? Those that are the different color. So remember, let's get going with that particular calculation, and then we'll be able to see it. So again, we've got the first one. Let's do the second one, which was 5 out of 8. 5 divided by 8. And I'm going to get the decimal fraction. I'm going to multiply that by 4 divided by 7. And we get an answer that as a decimal is 20,41%. So in terms of my decimal, 20,41%. So guys, here's what I'm saying to you. If I want to calculate when they are different colors, I need to recognize this percentage plus that percentage subtracted from the total will give me, so when I add all of these percentages, let's do it this way. If I say this one plus this one plus this one, what do we know about those? If we added all those percentages, well, it must equal 1, okay? And we want to know what the percentage of X or Y is. Remember that when we're asking for when there are different things, we're saying it's this combination, R yellow, red yellow, or yellow red, and it's an OR. So we are going to recognize we're going to use the addition rule there. But in this case, we're going to use the addition rule for the ones that are the same. So let's do that first. And I'm just going to find some space. 20,71 and 10,71 and 20,41. I hope I can remember those as I find myself some more space. And what we've said is this was 10,71. This was 20, just check on the calculator, 20,41. 20,41. So the first thing I'm going to do is I'm going to say to myself, let's find the probability of red, red, or yellow, yellow. Have you got that? We're wanting to see how these add up together. And if we do that, we recognize they are mutually exclusive. So this is the probability of red, red, plus the probability of yellow, yellow. And so if we do that, you'll see that it's going to come to these two percentages added together. And so on the calculator, I'm going to put that in. I'm going to say it's 20,41 as a percentage, but I'm going to do it as a fraction now, plus 0,1071 equals 0,3111, and I round off the fourth one to a 2, so it's 31,12%. So overall, we recognize that this probability that we've got of these two added together, because they were mutually exclusive, is 30 comma, just make absolutely sure, 31 comma 1. Let's make sure that we get that right. 31 comma 1 2. I'll just erase the 30 there and put it back into the pen. 31 comma 1 2%. Okay. Now, have I answered my question? Well, clearly not, because what I've calculated is the percentage of getting both the same. But this is the power of the complementary rule. Guys, if we use the complementary rule, we can subtract that number from 1. And so that is what we're going to do. So to find the different colors, to find this probability of either yellow-red or between those two, or we're going to say that probability is going to be the probability of red-yellow, or the probability of yellow-red, and that's going to be 1 minus that probability that we've just worked out, which was red-red or yellow-yellow. So we're going to subtract, and we're going to see what we're going to get. So here we go. Hope that we've got this all sorted, and we're going to say, we're going to take that value, and here's my little trick that I'm going to do. I'm going to multiply this by 1, but I'm going to make it a minus 1. In fact, let's just do the minus first. I want to take the answer, and I'm going to multiply it by minus 1 and see if that gives it to me right. That's correct. And then I'm going to add 1 to it. And guess what I get? I get an answer of 0.6888. So that's 68.89%. So my answer overall, the percentage of getting two different colors, is 68.89. 68.89%. Wow. That took some time to get going and to get through it, and we've used a lot of different rules. Now, you might say, but there's a shorter way to do it. And yes, there are other ways to do it. Please remember that you can practice each of the ways, and you will confirm that the ways that you've used will get you the same answer. So don't be afraid. Get your calculators ready and check, check, check. That's why at the end of a test or an exam, if you've got some extra time, you can not do it this method, but do it the direct method. But remember, when we calculate the probabilities, we've still got to do the OR sum to get them together. It doesn't matter whether it was red-yellow or yellow-red, but we could calculate it directly. Let's just do a quick recap and make sure that we're on track. So in this lesson, we've looked at tree diagrams. And within looking at tree diagrams, we recognize that the two things in the different stems are mutually exclusive. That means that if we're going to take the probabilities across the stems, they will always add up to be 1. So when we add those in the OR thing, the OR rule, that's going to give us a total of probability of 1. Of A or B is going to give us 1. Because we recognize that is going to be the probability of A plus the probability of B, and they're going to add up to 1. We recognize that for independent events, we've spent some time talking about those, the probability of the one's not going to affect the other, and the probability of A and B, if they are independent, they're simply the probability of A times the probability of B. And for dependent events, remember, that's where we get no replacement. Okay. Guys, dependent events, replacement. Okay. Please make sure you've got all of those things at your fingertips. The next time you get a tree diagram question, I bet you the probability of you getting it right is going to be much higher than 50%, maybe even 90%. From me, thank you so much. Goodbye.